Hi everyone. In this lecture, I want to go over direction fields or slope, direction or slope fields. And how we use them and how we can use them. Now, in the course, we know we're going to learn a lot of techniques to solve differential equations, but sometimes there is no technique to solve an equation, and well, numerically, it's probable. But for some differential equations, as you can see, I put, let us imagine you're asked to solve a first order differential equation and that you can neither find the solution or nor invent a method to solving it analytically. So sometimes we can get that. So that's when we go into direction fields or slope direction or slope fields to get an idea of the graph of the function. Now, before we do that, I want to review some calculus. In calculus, we learned how to graph functions, and then to graph a function, what we needed to do is to find the first derivative, and we know the first derivative is the slope of the tangent line at any given point. And if the derivative is positive, then we know the function was increasing. As you can see here, this graph here, f prime of x is positive, so f of x is increasing. When f prime of x equals to 0, you either have a max, a turning point, or you have a mean. And sometimes you have a corner. That's when the f prime of x does not exist. So we learned that from calculus. I wanted to review that here. So in calculus, given the function, we found the first derivative to get an idea if the function was increasing or decreasing, and the second derivative gives us the concavity, but we're not going to be talking about the second derivative here. Now, what happens in differential equations? In differential equations, we can't get the function. However, we know we have the slope of the tangent line, so we can calculate the slope of the tangent line at any point. And if it's positive, we know that the function is increasing, and if it's negative, we know it's decreasing. And if it's 0, then we know we're going to have a max or mean. So if I go over this, so a fact from calculus, this is what I just tell you, but let's go read this. A derivative dy dx or differential of a differential function y equals to y of x gives the slopes of tangent lines at points on its graph. A solution y equals to y of x of a first order differential equation dy dx equals to f of x must be continuous and differentiable on some interval I. So, and note that f of xy is known to be the slope function or the rate function. So the derivative, we can also call it the slope function or the rate function. So how can we solve this unsolvable function? Now, as I told you in calculus, we're given a curve function, and the objective is to find the tangent lines to the curve at any point. In differential equation, we reverse the process to find the solution curve from the tangent line. How does that work? So suppose that we have a point xy, and that represents any point in the region of xy plane over which the function f of x is defined. So function has to be defined. The value of f of xy that the function f assigns to the point represents the slope of a line. This line segment is called the linear element or the line element. So we can find, when we find at a point the value of f of xy, it gives the slope of that line, and that's at 0.23. So, and that's from this example. For example, we have this given. Now we know we can solve this differential equation. However, let's see what happens at 0.23. If we substitute, we get 1.2. So the slope of the tangent line at that point is 1.2 is positive. You know the function will be increasing. So, and here you can see the graph. So at that point, the slope is 1.2, and we know this line, we have a positive slope, so the function is increasing. So, and here, let me read this for you. The figure on the right, well, on the right, when I said on the right, that's what I meant. Shown line segment, or line element with slope 1.2 passing through the point 2, 3. From calculus, we know the solution curve also passes through 2, 3 because they share that point. So, and is tangent to the line element. Now, if we have a rectangular grid like that, and we find all the points or all the slopes at those points, then we can get an idea of the curve. So that's what the direction field is for. So now we call those the direction field or a slope field of a differential equation. So basically what we do, we find the value of the derivative at each given point, and then once you have a lot of them, you get an idea of the curve. To do this by hand is very hard, and I won't even give you this during the exam, but right now you can use Mathematica or MyMATLAB to kind of get that. The command for Mathematica, it's streamplot, and on the homework you're gonna see some examples. Please go over that. If you have Mathematica, try it yourself, and you get an idea of how that works. But by hand, probably nowadays nobody does that by hand, and I won't give you a problem to solve on the exam, however, by hand. However, get the idea and understand just the concept of direction field. So please do that and try some homework problems if you have the Mathematica. In this case, so for the same dy dx equals to 0.2 xy, we notice on the x-axis and y-axis, when we plot in the points, we get 0. So we have all horizontal tangent lines here. And if you have a grid, you can calculate on many points close to each other and get an idea of the direction of the graphs. So now, then the last thing I want you to know is this definition: autonomous first order differential equation. An ordinary differential equation in which the independent variable does not appear explicitly is said to be autonomous. If the symbol x denotes the independent variable, then it's an autonomous first order differential equation. So that's the way you write it. If f of y prime equals to 0, or dy dx equals to f of y. So this is only function of y and not x. As you notice here, if you have a differential equation like this, dy dx equals to 1 plus y squared, that's autonomous. And dy dx equals to 0.2 xy, that's non-autonomous. So please remember this, because we're going to be using this in the next lectures. You can take a look at the homework, and I did that with Mathematica. You don't need to use Mathematica during the exam. However, please understand the definition of direction fields or direction or slope field. Thank you for watching. I'll see you in my next video. Have a good one.